We've seen many examples of resistive networks where we have sources and we have resistors. In this circuit, if we have constant sources, we can expect to have constant voltages and constant currents. We assume that any changes to this network, whether it be by changing a resistance or opening or closing a switch, will have essentially an instantaneous response where all the voltages and currents will immediately become their new constant values. However, an RC circuit is a circuit that is a resistive network that includes resistors and sources and also includes a capacitor in its midst. A capacitor is a little bit different from a resistor. Its characteristic equation is thus: the current flowing into or out of a capacitor depends on the rate of change of the voltage of that capacitor. And thus, the current can change instantaneously, but the voltage has to be differentiable, and that means that it is continuous throughout its motion. So if you throw a switch that would change the capacitor voltage from one value to another, that capacitor is going to slow down that change in the circuit and will have what's called a transient response to that change in the circuit. That's what we're studying here. Recall that a capacitor is an energy storage device. It cannot produce its own energy. It can only store energy from some outside source, from some external circuit that must have some independent sources in it. The transient response of the capacitor is the behavior of the circuit while the capacitor is discharging, while it's taking the energy that it's stored and distributing that energy through the remaining circuit that it's connected to in order to minimize the change in voltage, to slow down that change in voltage as much as possible. However, after a long time has passed, and a long time has passed is kind of a vague term, but we're going to say it is approximately 5 time constants, and we'll define what a time constant is later. After a long time has passed, the transient response has dissipated, and the capacitor will reach a new steady state at which the voltage is constant, and if the voltage is constant, then the current must be 0. Since the current is the derivative of the voltage, if the voltage is constant, then the derivative of the constant is 0. A capacitor must have gotten its energy from some source. We would assume that the capacitor is connected to some charging circuit. If the capacitor has been connected to this charging circuit for a long time, then the capacitor would be in steady state. We said that in steady state the current would be 0, and so the capacitor is acting like an open circuit. There would be some voltage across the capacitor. That would be a fixed value that would be coming from this charging circuit. If there's a voltage Vc across the capacitor, then we know the energy stored inside the capacitor is this equation. There would be some current flowing in the resistor. If we have a voltage Vc here, then we would also have a voltage across the resistor. Those are in parallel, and so there would be some current flowing through the resistor, even though the current through the capacitor is 0, because the capacitor is acting like an open circuit. The voltage across a capacitor has to be differentiable, which means it has to be continuous. So the voltage before one instant has to be the same as the voltage after one instant. So if we look at the instant t0, when the switch is opened, isolating the capacitor from its charging circuit, the voltage across this capacitor was V0, the initial voltage. If we open the switch, the capacitor is no longer being charged by the circuit, but the capacitor voltage in that instant just before the switch is opened and just after the switch is opened has to be continuous, and so the starting voltage of the capacitor is still V0 now that the capacitor is isolated from its source and is going to discharge across this resistor. We can define the voltage across the resistor thusly, and we can say then that the increase in voltage here plus the increase in voltage there has to be 0 since we've gone around a loop. So we've applied KVL to the voltages across these two elements. The current through the capacitor is assumed to be in passive convention, and since there's no other place for that current to go, we can assume that that current is going to flow in through the resistor as well. And so we can say that this voltage across the resistor would be the resistance times the current from Ohm's law. And so we can take this resistor voltage and we can replace it using Ohm's law, realizing that there's only one loop, so whatever current is through the resistor is the same as the current through the capacitor. We're trying to take this whole equation here and rewrite everything in terms of constants like the resistor and in terms of the capacitor voltage and current, which are our characteristic parameters of the circuit. IC, the capacitor current, is this term right there. That's the characteristic equation of a capacitor. And so now we have one equation involving VC and its derivative and a couple of constants. We can rearrange this equation and move it around again so that we have all of our voltages on one side. VC is a function of T here. Presumably the capacitor voltage is changing with time. And we have the time side on the other. So we're able to take this differential equation and separate it so we have all of our V's on one side, all of our T's on the other, so that we'll be able to integrate and come up with a function for V of T. Starting from our separation of variables, we will change variables from V to the scripted V, from T to the scripted T, so that these are our dummy variables, and we can integrate from the starting instant T0, when the voltage was V0 initially, and we can integrate all the way up to some arbitrary time T, where we'll have some arbitrary voltage, which is a function of time. If I integrate 1 over V, I get natural log of V, and I plug in the top value minus I plug in the bottom value. That's what I have here. If I have two natural logs that are subtracted, I can divide those arguments inside one natural log. 1 over RC is all of a constant. That's not going to change, so that's still right there. And if I integrate dt, I get t. And if I evaluate at my endpoints, I get t minus t1. Now, if I take both sides to the power of e to the natural log cancels out, and I get this divisor is equal to e to this power. I multiply both sides by V0, and I end up with this equation for the capacitor voltage as a function of time. We have an exponential decay here that begins at t equal t naught. The capacitor voltage is V0, and then as time goes on, that capacitor voltage is going to die off. As t gets very large, the capacitor voltage goes to 0 because we've eliminated, with the opening of the switch, we've eliminated all the sources. The only energy in the circuit there is from the capacitor. That's finite, so as the capacitor discharges, the energy goes away, the voltage goes away, goes to 0 as t goes to infinity. We derived this equation for the capacitor voltage. Typically, T0 is going to be arbitrary, so typically we'll let T0 just equal 0. And in that case, that simplifies our exponential a little bit. And RC is the value we have there. Usually we'll put tau, the time constant tau, in the denominator, and we can see that we have RC in the denominator, so we can define the time constant as R times C is the time constant of the capacitor circuit. Recall that we said that a very long time is approximately 5 time constants, so this is how we know when the system should be in steady state or close to it. We assumed one capacitor connected to one resistor. If we have more resistors, use the equivalent resistance of the circuit connected to the capacitor. We found the capacitor voltage. If we know the capacitor voltage, we can find the capacitor current. This is the characteristic equation for the capacitor. C is the capacitance of the capacitor. That's known. If we take the derivative of this term, the V0 is a constant that will just sit there. The derivative of e to the minus t over tau, derivative of an exponential stays put, and then we get this factor from the chain rule, from the exponent there. We can simplify this a little bit, and we get this equation for the current of a capacitor in the natural response. Notice here that this is V0 over R. That is the initial voltage across the capacitor. Once the switch is opened, this voltage is held constant for just a moment as the capacitor begins to discharge. The current in that instant is the voltage divided by the resistance, would be the initial current that we would have. If we want to know the power dissipated by the resistor, the power is V squared over R. We know V for the capacitor. We found that. Divided by R, we can simplify that algebraically. And the total energy delivered to the resistor is the integral of the power. So if we count up the power at every instant from when the switch is opened unto infinity, we'll be able to find the total power, total energy delivered to the resistor. And as that energy is delivered to the resistor, that's energy that's leaving the capacitor. Note that as t goes to infinity, this term goes to 1, and the energy delivered to the resistor is 1/2 CV squared, which is all of the energy that was initially in the capacitor. So at infinity, all of the energy has left the capacitor, and it's been delivered to the resistor as the capacitor discharges. We can use linearization to approximate a function. If we have the voltage of the capacitor, we can find its derivative right at t equals 0. And so we can approximate this function as a linear function. The capacitor voltage is actually a exponential decay, but we can approximate it as a linear function that will be a straight line. You see that it's not a very good approximation. They don't match very well. The reason why we would do this is that this line here is crossing the horizontal axis at tau. When t equal tau is when this function equals 0, when we're crossing the horizontal axis. So you can look at an exponential decay, and you can approximate what the time constant is without having to do any curve fitting or getting too deep into calculations if you want to do just a quick estimate of that time constant. So to recap the natural response of an RC circuit, the first step is to determine the initial capacitor voltage V0. This is your starting point, and this will be the steady state voltage before some change has been made to the circuit, before the switch has been thrown. After the switch has been thrown, you look at the new circuit that the capacitor is connected to, and you calculate the time constant, tau, which is R times C. C is the capacitance of the capacitor. R is the equivalent resistance as seen from the perspective of the capacitor. Once you have these two values, you can find the capacitor voltage as a function of time. Once you know the capacitor voltage as a function of time, you can find the capacitor current as a function of time, and you can find any other voltages, any other currents in the circuit, any powers or energies being dissipated based on what you're being asked.